Hello, welcome to the Group 67 presentation. I'm Eric Rotger.
I'm Benjamin Sumners.
I'm Adrian Moat.
And I'm Natalie Cunningham.
Air pollution takes on many different forms such as gases, solid particles, and more. And as we know, all forms of air pollution is harmful to humans, animals, plants, and just the overall environment. So that's why Group 67 decided to explore correlations between air pollution and other major issues a country may face. The top four major issues the group decided to focus on were child mortality and health, tuberculosis, health expenditure, and unsafe drinking water services. All of our data sources were generated by the World Health Organization, and listed on this slide is the names of the dataset we used to explore our problem statement from before, all of which have been clearly referenced within the repository.
Okay, so I decided to examine the relationship between air quality and child and infant mortality rates around the world to see if there was some sort of correlation linking the two. As you can see here, the initial child mortality and air quality data sets were quite large and have a lot of columns that I did not need. An issue with the air quality data set was that some countries had a lot of entries in the table because they had multiple air quality recordings for different locations, with some countries having a lot more than others. Natalie had some neat code to clean up the air quality data set by averaging each country's air quality data, so each country only had one entry. As you can see here, there's a lot of entries for Australia, only one for Albania. I adapted this code to the child mortality dataset because I faced similar issues with countries having multiple entries. I then reduced each data frame to only the columns I needed and merged them into one frame containing the country, its total child deaths for both sexes at all ages, and their PM10 and 25 levels. That's that infant air.head data frame down here that I created. I then attempted to visualize this new data frame to see if there's any sort of correlation. Using this new clean data set with only the requisite data, I attempted to visualize if there was a trend using scatter plots and a linear regression line. I created two plots, one for PM10 and one for PM25. You can see in the code my scatter plot and my regression line for both data sets. And my results, as you can see, both graphs, oh, I need to move this, sorry. As you can see in both graphs, there is a distinct cluster both close to zero on both axes, indicating a strong connection between lower PM levels and lower child death rates. That's this cluster here. You can see in the green plot of PM25 and child deaths, there is a general trend suggesting higher PM25 rates correlate to higher child deaths. But interestingly, there are a lot of instances where a country has low emission levels, but still very high child mortality, like these ones up here, where the PM25 isn't too high, but still very high child deaths. This is shown even further in the red PM10 scatter plot, but there is still an evident linear relationship between the two.
Hi, so today I'll be talking about tuberculosis and its correlation with air pollution. So this first slide here shows all the results that I had gathered through my extensive research of the data gathered from the WHO website. So pretty much, as I've put here, the results gathered from the extensive research and data visualization bring forward evidence of a correlation between higher cases of tuberculosis in areas with worse air pollution compared to those with lower rates, obviously, of air pollution. So as you can see here, in Afghanistan, there is quite significantly high cases of tuberculosis. But then, if you look at Zimbabwe, they have more consistently higher cases than in Afghanistan. So as I've done in the first slide, the first part, first image, that basically is just showing you all the data that I got originally and then just put straight into the table. And then the second image is showing after I've gotten that data, I've gone and simplified it and just made it look a little bit nicer. So, yeah. Anyway, so the next slide, sorry. Cool, so the methods that I used in order to gather all this tuberculosis data, obviously the, tuberculosis.head, just displaying all data from the data source file. And then when I did tuberculosis _ simplified, that is just tuberculosis the original data set, I've gotten that and then narrowed it down so it's just the important fields: country, number of incident tuberculosis cases, and the year. And then I tried to, but I wasn't successfully able to complete it because it kept erroring. But I put my code in here. I tried to make it even simpler and then try and delete all of the null values so it would look a little bit nicer. But unfortunately, I wasn't able to complete that part because I wasn't able to figure it out. But yeah, that was basically my conclusion, that it does show significant evidence of higher tuberculosis cases in areas with higher air pollution. Thank you.
So I decided to look at the correlation between air pollution and health expenditure per capita. Health expenditure relates to the amount of money spent on an individual's health in the average year, adjusted by purchase power parity, which gains an accurate comparison across all countries in the world. I also decided to look at the average number of hospital beds per 10,000 population to see if there was a correlation there. So the datasets I used had many unnecessary columns and measurements that I didn't need in my analysis. So I had to drop those unnecessary columns. I renamed the row and column indices so that they're the same across all datasets. My air pollution dataset also had multiple rows per country, so I grouped them together by the average so that there was one row of data per country. I then combined my datasets into one dataset for easier comparison. I looked at the summary of the data to get a better feel of the numbers that I was working with. For visualization, I used a simple scatter plot to see if there was an obvious trend in the data there. I then used 3 predictive methods: linear regression, k-nearest neighbors, and hierarchical clustering. So the scatter plot visualization resulted in a slight hyperbolic trend, as you can see here. The predictive models were highly inaccurate due to the non-linear trend and the lack of clear clusters in the data gathered. However, the most visually accurate model, even though the accuracy of the model itself was 0.1, used k-nearest neighbors to predict the health expenditure of a country based off of their particulate matter levels. Regardless of the lack of clear trend in the data shown, the results show that the country that's spending the most money on health have very low PM levels, and the countries that have the highest PM levels spend the least money on their health per capita. Ta-da!
This portion of the presentation will explore whether or not air pollution has any correlation to the total percentage of a country's population with access to a safely managed water service. These types of water services have been defined by the World Health Organization as water that is available when needed, free from contamination, piped water, water from boreholes, protected dug wells, protected springs, rainwater, or even delivered water. The Jupyter Notebook, which explores this topic, includes methods such as data cleaning and visualization of the data in order for it to be more readable and easier to work with. Then this notebook goes on to make use of a linear regression model to predict a correlation between water services and air pollution, and then evaluates its effectiveness with an accuracy score and matrix table. 2 data sets were used in this analysis, one which showed the total percentage of a population that has access to a safely managed drinking service, and another which shows the level of particle matter 10 and 25 from various countries. After cleaning the data, there were 3 main questions asked and explored. The first question was which countries have a high PM10 and PM25 level, and in this instance, I defined a high level as anything greater than the 3rd quartile range of the average levels for each country. And this resulted in 26 out of 197 countries in the dataset having a high PM10 level, and also 26 countries having a high PM25 level. Some countries were on both lists, some were only on one. The second question asked was which countries had a population of less than 51% who have access to these safely managed water services that I mentioned earlier, which after some exploring of the data, it was concluded that about 32 of 197 countries lacked this type of safe water services. And finally, is it reasonable to assume that there is a correlation between a country having a high level of PM10 or 25 and the same country having poor access to a safely managed water service? Using a linear predictive model on a fairly balanced data set, Is it true that if under 51% of the population lack safe access to water services, it meant having a high PM10 or PM25 level? This model scored 70% with sklearn's accuracy score, and also the majority of results on the confusion matrix table were labeled either true negative or true positive, meaning it's very likely there is in fact a correlation here between a country having a high PM10 or 25 level, aka high air pollution, and the same country having under 51% of the total population having access to these safely managed drinking services. In order to sum up Group 67's findings, it is important to note that we were looking for correlations of air pollution and other major issues in a country, which means this does not imply causation. And from our analysis, we revealed that child mortality, tuberculosis, health expenditure, and unsafe water services all correlate in some way or another to air pollution. Thank you.